Hey everybody, welcome back to Info 3370, studying social inequality with data science. So today we talked about writing a custom R function. And this is a really useful advanced skill in R because it can take tasks that you might carry out repeatedly on your data set and package up all that code in a function so that you can call that function to do those tasks many times without copy and pasting your code everywhere. So what's a function in R? A function is an object in your environment. It has arguments and it returns something. So to see this, let's begin with a really simple function. I'm going to call this function double a number. And this is going to be a function of some input x. And inside this function, we're going to do something with x, and then we're going to return something. Okay, so double a number is going to be the name of the function. And we're assigning to an object, double a number, a new function. And that function has an argument. That argument here is x, which is going to be a numeric value. And once we get inside the function, these curly braces tell us what goes on in the function. So the first thing we're going to do in the function is make a new object twice x, which is going to be 2 times x. Now twice x is not going to live in our global environment. This just lives within the local environment of this particular function. And then once we have twice x, we're going to return twice x. Okay, so I'm going to go ahead and run these lines. And now we see that double a number appears up here in our global environment as a new function. And if we call this function, we can type double a number. And look at that, it tells us the argument is x. And maybe x equals 2, and we get 4 when we double that number. So if you know how to write this double a number function, then you basically know all the key pieces there are to know about writing functions in R. You could have multiple arguments, you could have a more complicated return than this, but really at its most basic level, a function is just an object you define that takes some arguments and returns something. So why would we use a function in a real setting? Often we use a function when there's not a canned procedure that comes already with R that will carry out our process in a really simple way. So sometimes we're doing something super complicated with our data set, and it's something we know we're going to do multiple times. And that's when you really want to have a function. So let's go over here to some real data. So I'm going to load the tidyverse and load Haven, as we always do. And I'm going to load this prepared DTA file. So what's in this file? This is the same data that we've been working with a lot in class recently, where we have the current population survey available through IPUMS. And if you don't have those data, you can look back at the previous videos to see how to get those data. So what we have here is a bunch of respondents to the survey in years from 1962 to 2022. And for each respondent, we know whether they finished college or whether their education is less than college. And that's a variable we created in a previous video. We also have the income of that respondent in the past calendar year, and this other column that to now we've been ignoring, ASEC weight. And so what is in this column? The ASEC is the annual social and economic supplement, so the big annual March survey from which we're getting these data. And the weight tells us how many people are represented by each person in the data. So we could think of this person in line 1 as representing 3,224 people. Meanwhile, this person in line 7 represents more like 1,598 people. So whatever's going on with the person in line 1, if we want to make claims about the population, is way more important than what's going on with the person in line 7. So how did this come to be? When they designed the current population survey, they want to be able to make claims about the unemployment rate nationally and also within each state. And so one important reason why weights are unequal is that they have to oversample people from the less populous states. So you got to have enough people from Wyoming in order to estimate the unemployment rate in Wyoming reliably. And by consequence, this means that your probability of inclusion in the current population survey is about 10 times as great if you live in Wyoming as it is if you live in California. And so when we analyze these data and ignore the weights, we're giving too much attention to the people who only represent a few other people, and not giving enough attention to the people who really represent lots of people. Now I'm slightly oversimplifying by just focusing on the states, but the current population survey is a really complex survey design, And so that's why we trust the people who designed the survey to create this weight variable for us that tells us how many people are represented by each row in the data set. Okay, why did I go into all that? You'll remember that with these data previously, we summarized them by quantiles of the distribution. So we took the prepared data frame and we grouped by education and year, and then we summarized and said, like, what's the 50th percentile of that distribution? It's quantile Inc. wage 0.5. And once we ran this line of code, we now have, for every education by year group, the median of the income distribution. But wait, I just said that the survey weights are super important, and here I just ignored them. I treated each respondent as equally important. So perhaps we want to summarize the distribution by the weighted median rather than the unweighted median. In other words, we want to find the income value such that 50% of the weight is on people with incomes lower than that income, as opposed to 50% of the people having incomes lower than that value. So how might we do that? So this is going to be more complicated. I'm going to write a little bit of complicated code here. And remember, the takeaway is not how to make a weighted quantile. The takeaway here is that we can take this very complicated code and then write it in a function. And ultimately, we'll be able to summarize by weighted quantiles just about as easily as we were above using unweighted quantiles. Okay, ready for the code? So we're going to start with our prepared data frame. And actually, to make this easier to look at, I'm going to make a subset, which is the prepared data frame restricted to those for whom education equals college and year equals 2022. So let's look at prepared subset here. Okay, because after all, up above we were making estimates within each subgroup defined by education and year. So here, to simplify, let's just focus on one subgroup for now. Okay, so if we want to say something about quantiles of the income distribution, a good first step is to order this data set by income. So I'm going to take my prepared subset and I'm going to arrange by Inc. wage. Arrange is a new function we haven't covered yet in the tidyverse, but you can see pretty clearly what it does. It takes this previous data frame and it just reorders the rows so that the smallest incomes come at the top and the biggest incomes come at the bottom. So let's call that sort the data by the variable of interest. Okay, so after arranging, now we want to calculate the cumulative density function, or CDF. Okay, so if you've taken probability and statistics, you know that the CDF tells you the probability that a random variable is at or below any particular value. So in this case, we want to figure out the probability that the random variable income is at or below any particular value. And the distribution of income is determined not just by the distribution across rows, but the distribution over these weights, asec weight. So here we're going to do a slightly complicated mutate step. So we're going to mutate to create a cumulative weight and also a total weight. And then after that, a CDF. Okay, so let's start with this cumulative weight. The cumulative weight is going to be the sum of the weight that we have reached by each particular income value where we might stop. And we can calculate that with the cum_sum function. And we'll take the cumulative sum of asec weight. And if you're not familiar with cum_sum, you can always do this and see how this works. So this takes in a vector and returns a vector, which is the cumulative sum of the vector that it's handed. That's a mouthful. Okay, then the total weight is the sum of asec weight. Great. Then the CDF is going to be the cumulative weight divided by the total weight. Okay. So that was a lot. Let me just run a little of this. Oh, look at this. I have an error. This needs to be cumulative weight. Okay, great. So we've run that. So here we have the weight on the first person. The total weight we've gotten to by this point is that same value. Then the cumulative weight in the next line takes the previous cumulative weight and adds the new weight. So 5,005 is the total weight on observations with income at or below 52. And look at that, there's actually a tie here, so then you keep going, add this 2604, and 7609 is the cumulative weight on observations with income at or below this value. The total weight is the constant over everybody, so that just is the entire sum of the column. And the CDF says what proportion of the total weight have we reached by the time we reach this particular income value. So the total weight tells me like where we are in the overall distribution. Now if we want to summarize the median, that's going to be the income value for which the CDF is 0.5. So next we're going to move to our next step, which is filter to CDF above the quantile. So we're going to filter here to CDF greater than or equal to 0.5. So let's run that, and now we see we have these observations where at least 50% of the total weight is on observations with incomes lower than this particular value. Okay, great. So next what we're going to do is we want to take this very first observation, because after all, to estimate the median we want to be at or above 0.5, but like no further up than needed, so that we have 50% above and 50% below. So keep only the first row, and we can do this with slice head n equals 1. And this tells R that we're going to slice off the bottom of this data set, keep only the head part, and keep only that first row. So when I do that, I get now this new table that has just that one top row. And now we're getting really close. So let's call this result df for data frame. Okay, and then the median we want to report is result df dollars inc wage. Okay, and because this is pulled out of a table, it has like all this extra information, and if we just take the first element here, we get back to like just a number. Okay, that was it for the extremely complicated bit of code. So to estimate a weighted median, we began with a data set, arranged by incomes, calculated the cumulative density function, then filtered to cases where the CDF was at least as big as 0.5, then kept only the first row. So now, what if we don't want to keep writing this code again and again? We can now put this within a function. So let's call this function weighted median. It's going to be a function of some data. And here, our data might be prepared subset. And we can pull all this up into the code here. And so instead of calling this prepared subset, let's go ahead and call this data. So now we could return this income value at the bottom, and let's see where we are. So now if I do weighted median of prepared data equals prepared subset, boom, I get back that weighted median estimate. And you could imagine doing this on a different subset. So you could say, now we're going to look at 2021, make a different prepared subset, and we see that in 2021, that weighted median was $85,000. Okay, so now I'd like to generalize our function a little bit. So instead of focusing on data in general, let's suppose that we want to hand it some variable to summarize, x, a numeric quantile value w, and then a numeric vector w, the quantile value q, and a numeric vector w for the weights that go with each observation along x. And then let's suppose our first step here is to create a data frame with x equals x, q equals q, and w equals w. You know, we don't even need q equals q here. We could just have x and w. Okay, so this says you're going to pass it some vector of numbers, some quantile you want from those numbers, and some weights on all of those numbers. So now because we're generalizing, we're not going to arrange by inc wage in particular, we're going to arrange by x. And this is good if we want to take the median of like hours worked or something, which we wouldn't want to refer to as inc wage. Okay, then we're no longer going to focus on asec weight. We want to generalize to any arbitrary weight w. And then we aren't going to focus just on the quantile 0.5, but any particular quantile value q. And then finally, instead of ink wage, we're going to have x here. So let's look over this code and make sure I don't have any ink wage references or any 0.5s. I think this code is pretty general. Okay, last step. Now that we've generalized over q, we should call this thing weighted quantile, not weighted median, because it could be used to estimate the 10th percentile or the 50th or the 90th percentile, for instance. Okay, so now we have weighted quantile. And now, so we don't get confused, I'm going to remove weighted median from my global environment. Okay, so let's test out weighted quantile. So now our argument is different. Instead of prepared subset, we might have x equals prepared subset, and we're going to pull out the ink wage variable. Q equals 0.5, and W equals prepared subset. We're going to pull out that asec weight variable. So let's look at that, and we see that the 50th percentile here is 85,000. And if we switch to focus on the 90th percentile, we get 2E5, I believe that's 200,000. If we focus at the 10th percentile, 43,500. Okay, so this is great because now we have a function that takes in vectors and the quantile value that we want. So now let's take what we were doing with unweighted quantiles and do that with weighted quantiles. So now we have our full prepared data set. We're going to group it by education year, and then we're going to summarize the 50th percentile with now the weighted quantile, where x is ink wage, q is that quantile value, and w is asec weight. And if we run this, we now get, for every education and year subgroup, the 50th percentile, where the percentile is over the weighted distribution of incomes. And because we've written this up in a function, it's now easy to copy it over here and make the 10th and the 90th percentile. And if I was doing this for a ton of percentiles, I might put this in a for loop or something, so I wasn't copying and pasting at all. And so now running that code, we get to see that we have pretty similar to what we had the other day. So we have the 10th, 50th, and 90th percentile, but now we've appropriately incorporated the survey weights so that our estimates are based on the weighted distribution of incomes that's designed to be representative for the whole population. So that was a lot. The key here was that there was a complicated procedure we carried out with data. And we first did that in one special setting, and then we generalized it to a function that we called weighted quantile. We stored that function up here in our global environment. We tested it in a particular case, and then we applied it over multiple quantiles and in lots of different subgroups, neatly within the same piping procedure that we've been using all along. But the big idea here was really quite simple, which is that in general, if you're going to do any process to data, if you can wrap that process in a function where there are some arguments, you do things with those arguments, and then you return something, this is great because now you can call your own custom function to do that procedure, and it's really helpful when it's a procedure you're going to use multiple times in your code. So if you'd like to read more, I would encourage you to take a look at chapter 19 of the R for Data Science textbook, which has a whole bunch of nice things about functions, what they can do, when they're particularly useful, and ideas like how you ought to name them. So I would really recommend that reading. And that's all for today. Good luck as you go out and write your own functions.